I want to start a little bit of some questions. Are there any database administrators over here? All developers. Okay, good. This was the intention of this talk. We're not going to talk about database internals or too specifics. We're just going to cover a couple of stuff. And a little bit about myself. So this is the cool new thing from the LinkedIn that you can actually add me. And also my Twitter handle is AskDBA. I work for Percona, and I've been in database business over 2 decades. And what I mean by 2 decades is over 20 years, 23 years to be exact. I've worked in large enterprises, done enterprise database administration for very large corporations. Then a moment came in and I switched to open source databases, specifically on MySQL. For the last 10 years, I work in MySQL or MySQL-oriented applications, databases, systems, and I focus mostly on MySQL. From my side of the things, I am at the operations. So we do global operations for databases and manage customer databases all together. What that means is we basically take care of all the databases for our customers. And I manage a team of 9 DBAs around the globe. And then they're 24/7. And we take care of all the incidents and database operations for large customers. And so I do database administration. I build teams. Also, I do a lot of teaching and speaking activities. About my company, Percona is an open source oriented company. It's actually intention to be unbiased support for open source. Currently, in its arsenal, there's MySQL, MongoDB, and PostgreSQL. And within these service units, there are 4 main service units in Percona. 3 of them are services. One of them is engineering. So the services split in support, managed services, and software, and also consulting. And the other one is the engineering, where we actually have our own software. So Percona started as a consulting company, but then it turned into a software company that actually has its own fork of MySQL. So MySQL upstream owned by Oracle, and then fork is Percona. So there's a server called Percona Server. You can download, install, open source, and then use it. Also, it comes with a lot of tools. There's a toolkit called Percona Toolkit that actually helps you manage your database administration. And so we also support other distributions like MariaDB. And lately on the cloud side, we have Amazon RDS, Aurora, and those support and tools that we manage. It's been in the business for almost over 12 years. This year was 12th anniversary. And then we have a very large customer base. That's what Percona is. So what are we going to talk about today? This is how I designed today's talk. I'm going to talk about indexing basics, just talk about indexing fundamentals, and how we find and identify the slow queries in MySQL, utilize some of the tools, advanced indexing, and there's more tools. So I split it up into 5 different sections. And if you have questions in each section, we can stop and then discuss a little bit, or we can talk about it at the end. If time is not enough or you're too hungry today, we can talk in the speaker's corner later on. So please come find me. So let's start with the indexing basics. So what does it do, like index? Why do we need index? Basically, we want to speed up our queries, our lookups. So your selects are going to be faster. That means your application is going to actually return data faster. And with the index, you can actually reach that data faster, just like in the old phone directory, right? You go to K and then find the names that started with K. That's what the index does. In the database world, there's a thing called Optimizer, which I will get into that high level, very high level. that actually makes a decision to use which index, or if there's an index, or some other options we will talk. So that's the indexing basics. And always we have to start with why. Why do we need indexes? Basically, data is on the disk. It's cheap, but slow. So if you actually read, just like in the old days, the mainframes, the old systems, some of you are not old enough to know that the files were sequentially read, they would be able to tell where that file handle was. And this goes back to the days that I started. And then when we switched some of those old systems, they would ask me, how far did we go? I don't know. You can guess, but you don't know exactly what the pointer is. Because databases, the modern databases, use different techniques like read ahead. So what it does is it actually reads pages ahead of the time, knowing that it will read more. It brings those to the buffer, and then reads from the buffer. That gets you the faster data access. It could be in the memory, like everything else. It's already in the memory because all modern databases, all modern RDBMSs use memory as a faster access, but it has its own different techniques like LRUs and the mutexes and so forth. We won't get into that. So basically, index is to answer for an access faster data. So how does the index work actually? In very high level, it has pointers, and the pointers actually does a traversal, and then it will follow the leaf chain and fetch the table data that points to the original data. So the index has a data page that is a link, and that pointer actually linked to a page. The difference between the normal data page and the index page is just as the pointer that goes to the data. So what it does try to do over here is actually it tries to do minimum hops. So at minimum I/O operation, you go to the lower number of the leaf nodes and then do a faster index traversal. That's what the index does. And the leaf nodes works this way. Establish a double linked list and then connect those leaf nodes, and then that points back to the indexing columns or indexed columns. So in the database, in the table, there are multiple columns, but you don't necessarily index all the columns. You only index the necessary columns. And you only need a pointer for those index columns. The other point over here in this leaf node concept is how the index pages are maintained. Because the data is not static in the database. So you have inserts, deletes, and updates, and those pointers will change. The leaf nodes actually maintain the links. So that way, you don't actually have to forget the pointer where it was. This would actually cause a corrupt index, where it nowadays rarely happens, or fragmentation that in the modern databases that doesn't happen. We'll get into that also in MySQL world. The reason I have some experience with other RDBMSs is some RDBMSs in the indexes you had to actually rebuild, recreate to maintain a healthy leaf nodes. So very common indexing structure is a B-tree indexing, known as binary tree or the balance tree. This allows search, sequential access, insert, delete, and logarithmic time. So it's basically, that's how the traversal goes. And the node can have one or more children, and the way it actually handles is it has the pointers, and that goes to the nodes. And so this is the B-tree structure. So every index is not actually fast. There are a lot of cases in the databases that it could be very slow. One of those is low cardinality. Actually, if you were at the Elastic talk this morning, Philippe also touched base on this. Low cardinality is bad for indexing. So if you have a field on male, female, where half of the data is male, the other half of the female, that's a bad index. I'll show you some examples on that, but that's what it means by low cardinality, is actually number of occurrences is less, so your hit ratio will be very low, and making an index on that field is going to be slow. You can ask yourself, oh, I have an index over here, why is my data is returning slow? Because the database has to go through all the rows that actually has a very low cardinality. So if it's a large data set, it's the same thing. Your large data set is not a very healthy thing. That actually is also bad for the index, that it has to maintain large set of index, and it has to bring all of that into the memory and then process it and does multiple hops. So it's not very efficient. If you have in a large query, if you're doing a lot of joins or it's coming from ORM, you might have been hitting the multiple indexes, and then scanning through the multiple indexes can be very slow. Rather than stage your application and index through, and then get the result set, index through, and then get the result set, index through. That will be much faster. Looking for a suffix, of course, you need to look for the prefix mostly. Non-laden column lookup, I'm going to get into this because this is a major indexing technique. Data type mismatch, oftentimes you actually, developers mix strings with the numeric values, and it causes a lot of headache for the database to decide what is what, because database doesn't know basically what data type it is at the time of the execution. The other thing is a character set correlation mismatch. This is we live in a global world, and we have had a lot of cases where the databases are set to local correlation, not thinking that company or the business will go global, or have international users attached to it, and then they actually face this. Of course, there's UTF migration that is happening. The new databases are created with mostly UTF character set code. That is not a problem anymore, but this still, we see this a lot. This still is a slow index lookup issue. The other case could be, I'm talking in the MySQL world, it could be a bug related to index, bug related to optimizer, bug related to the engine. These are three separate things. It could be PostgreSQL, MySQL, or something else. We also find some bugs into that's actually leading slow index lookups. So let's take a look at over here on the optimizer side. Okay. This is, I took this one from Oracle directly. So the optimizer in high level, it works within an engine. There's a daemon called optimizer. Actually, it makes a decision on the query access. So the optimizer has a cost optimization technique that actually gives a number to the query, and based on multiple information. And one of that main information that it actually makes a decision is the statistics. So if you have a table that has an index, database keeps statistics about that index, about the cardinality, number of rows, row size, etc. And then based on that, if there are joins and a table scan, it makes a decision which way to choose. So we said MySQL Optimizer is a cost-based. Again, most modern RDBMSs, all of them use cost-based optimizers. This doesn't change the Oracle, PostgreSQL, or others. And it assigns a cost for a select operation, and then chooses the alternate plan, and then seeks the lowest cost. So in some cases, you might have multiple paths to reach the data. So it will choose the lowest cost, cheapest, and the fastest method. And the cost model works like this. So it has an access methods, and then join and a subquery. And also it has the CPU I/O. So as MySQL developed over the years, right now it's 8.0, the latest version. The cost model configuration is added on 5.7. So they keep adding new features to the optimizer, making more complex and more reliable in terms of choosing the right cost model. So in the metadata side, there's row and index size, index information, and the uniqueness. And it makes a decision based on these. The result is cost estimate plus row estimate, and then it will make a choice to go which path to choose. The next thing in the MySQL world is we actually, how do we find slow queries? I know you are mostly on the development side and you don't deal with this, but these are the known methods or the ones that we use mostly. The slow query log. So the slow query log can be configurable. If you set the slow query log to 0, it will record all the selects that are coming in. That means 0 seconds and more. Okay, let's do a little quick poll over here. What is the accepted query return speed, the duration that you would accept? How many milliseconds? It depends. No, in this case, it doesn't depend, because if you don't return your data fast, that user will go somewhere else. So you want to the fastest return from that select statement possible. But in my experience, mostly the web applications, the data that's actually retrieved from a database needs to be 500 milliseconds or less. So I would actually look, any query that takes more than 500 milliseconds, that's definitely a slow query. The queries that are actually between 0 and 500 milliseconds are still slow, but those are manageable. You could probably tune those. But if the query is taking more than 500 milliseconds, 750 milliseconds, that query is bad, or that application is pretty bad. And if you add up to the time that the person clicks on a select or an application function, there's a processing, there's networking, there's a CPU cycle, all of that, if you count it in, that's more than 2 seconds. And I go by somewhere else. So that's why slow query is very important. There are other techniques, but this one is the most common. That's why I put it over here. The other one is the open source tool, PMM and Query Analyzer. This is something I'm going to explain a little bit more in detail. You can network sniff. Basically, if you read the packets, TCP packets, that goes to the database, and between the database and the application, you can actually capture that information without the query log. And there are other licensed products out there for other enterprises. MySQL has its own version of MySQL Enterprise Manager in Oracle's, if you have the non-open source version of it. The other most popular tool is Vivid Cortex. They provide a great solution for that. And analyzing slow queries. There's SolarWinds, Monarch, and there's more. But I would start with the slow query log, and that's where I would start, because that's where the information you're looking for. So, okay, these are the slow query. Where the slow query? These are the tools that are available built-in or externally. So MySQL comes with the explain plan. Basically, you can run any select statement with an explain and see what it does. To interpret, you may have to look up some things, which I will show in a couple of minutes. But explain plan can be in tabular. It'll show you in like a select statement. It's now on 5.7 onwards. It's a JSON format. You could actually take that. You could dump it to a different data store. MySQL Workbench is free. You can download from Oracle. It can also visualize. Or you can just run a query within the database using performance schema or the MySQL sys schema. So there are a lot of examples on the internet. You can actually use those and then select those. If you're using a version that is greater than 5.7, you have more information. The older versions did not have that much of an information within the performance schema. Actually, performance schema was introduced in 5.6. Also, there is a technique you can actually enable optimizer trace within the database, MySQL Workbench, as we said, or from the command line, you can actually filter out the sort and the handlers. You can see that. So you can reset that per session, get that information, and you can see if it's doing a index scan or a full table scan. So these are the tools that is available. The one that I recommend right now is the PMM. PMM is an open source product that is Percona's. It's a Percona monitoring and management tool. One of the modules is a query analyzer, so it can actually do slow query analysis, and then it'll give you the list of, there's an example, list of queries that are actually running in a database. So this is a test, and it's captured from that test screen, and you can see the load, the count, and the latency, all of that. As you can see over here, there are some very, long queries over here from our poll a couple of minutes ago, 2.5, 2.15. So those are definitely a slow query. So you can drill down the server history. There is the query count, and then log time, and then you could look at all these statistics, and then visually it's easy to do that. Also, you can have other metrics like the query count, how many times it ran, and this is another thing that when we are doing a query analysis, query can be fast, less than 500 milliseconds. It could be 50 milliseconds. But if you run that query for 50 billion times, that's going to be a slow query. You need to find something about that. And that's what the other thing is, a query count and how many times it happened. You could have a query that's running 10 minutes, but it could be a bad job that's running on Sunday at maintenance window. So that's why the count is important. Also, the query analyzer can also give you the fingerprint of the query that you're running, and also the explain plan. So in this explain plan, if we actually took this select statement, select C from SP test, in a command line and ran explain select C from SP test where this and that between, and order by, it would give us this in a tabular format. And it said over here, using the primary key, it doesn't have this information. Number of rows is 1, and using var close and a file sort. File sort is because of the order by. We will talk about that also, because that's also important to know. Okay, so the explain plan has, we gave an example over here, real quick, and what the explain plan actually can give us, and this is from the Oracle MySQL documentation page, and the columns and the JSON name and the meaning of it. You can see the select identifier, it gives an identifier to each select, and then the select type, it will give you the options, and then you can see what's important over here is it uses the possible keys over here, the possible keys. So if you have multiple indexes and then using which index, and basically trying to figure out which index it's using, is it the right index, you can actually see it from here. So we're no longer blind in the database world. We know what the database is doing. You just need to look or know where to look, and basically you can figure out. This is called top query review. We actually analyze these top slow queries regularly, and then we modify those or let the developers know what optimization we can make, and then basically take the database outside of being a bottleneck. So the other format is JSON, and there's an example over here. These slides will be available, by the way, so you can download it later on. I'll upload it on the SlideShare also. It will, if you type in explain format with the JSON, it'll put it over here. Why this is important? There is some development or DevOps type of work can be done on the slow queries, and you can basically pipe this information into a data store that is a document store, and then you can analyze or run more complex queries against it. Why I say this? Because there are some companies that produce a large amount of slow query information. And analyzing this on a small scale is different than analyzing or storing in a different storage is a different thing. And also, with the continuous integration and continuous development, you could be changing your application too often. You want to see the changes. It's good to store all that information so that the fingerprint of the hash of the query is captured. You can compare these two later on if it made any changes, slowdowns or ups. We call that a pre and post application review. We do that with our customers, and then we actually take a snapshot of the environment. They go in a maintenance, and then they release a new code, and then we compare the differences if there's a problem, spikes or slowdowns. The other tool, so anything that starts with a PT is called Percona toolkit. So the Percona toolkit has a lot of tools. Look up on the internet if you haven't seen it already. PT Visual Explain also will give you a little bit more meaningful tree-like output, and you could see the possible keys. This is primary, that calls a primary key, and then the key length and the address ID is the 2, and what's the join. It's looking like it's a little bit more visual. There's more tools that actually visualizes, but that's what it is. Going back to the cost-based access method. So finding the optimal method, check if the access method is useful, estimate the cost, select the low-cost access. Don't forget this, because if we forget about this, then we're forgetting about the statistics. So I said MySQL doesn't need to rebuild indexes, but it needs to rebuild the statistics. So in all the cost-based optimizers, Oracle or PostgreSQL or other databases that actually is running on a cost base will have to update the statistics, including SQL Server. So in this case, you need to actually remember that the statistics needs to be constantly updated. So MySQL, the newer version of MySQL, automatically does it. But sometimes it doesn't do it, so you have to do an analyze table. That's another command. You run that, and then it updates the statistics, and then the queries start running as they should. Okay, the way the query execution works, just to remember over here, so it does a table scan if there are no indexes. If there's an index, it'll do an index scan. It'll do an index lookup. And then the range, you're looking for the between ranges, and then index merge, and then loose index scan. So these are the steps of the query execution. So we will go into the indexing best practices. Okay, we have also 10 minutes. I know you're starving, but we have 10 minutes. So we need to always have a primary key. Why do we need to have a primary key? Because the primary key is the physical order of the table. Sometimes it's called a clustered index, and it actually puts the data in the disk in a physical order. And it keeps track of the data, so you always need to have a primary key. The problem with MySQL, well, it's not a problem, but by design, if you don't assign a primary key to a table, it will create one. Basically, it will use one primary key auto-increment value from its system database, and it'll use that as a row ID for that table. And the problem with that is, if you have more than one table without a primary key, they all use the same, which causes a global mutex. It's a global lock, basically. If you have 100 tables without primary keys, they're all using the same auto-increment value in the global database that is actually competing each other. There is a document about it. I will share it at the end of it on the references section, written by Jeremy Cole in 2013. Just prior to coming over here, flying over here on Thursday, we checked it on the MySQL version 8's source code. It's still same. It hasn't changed. So if you install a MySQL and you're designing a database, creating tables, create a primary key for it. And the fastest lookup is always primary key. There's no faster than that. The other best practice we have over here is single index with multiple columns. So leftmost first and each additional field. So if you have a primary key, let's say there's a customer table, customer ID. If you have a primary key on first name, last name, you actually put the first name, last name. You don't put the customer ID in there. Customer ID would be a primary key in that sense. So create the ID as a primary key, ID fields, numeric, and then create the text fields as a separate. And when you're searching for first name and last name, you create a composite key. Don't create an index with a first name index and then a last name index. This is much more efficient because those each additional index will have a primary key as part of that index. What you would do is actually, if you have customer ID, that's primary key, first name, that's a different key, that already has the primary key, and you create another index called last name, that would be actually third index, you're actually duplicating the primary key in 3 different spaces. That's more storage, and that's more, I've seen tables that has a bigger index than the original table space. Because of the row length, if you actually have a large character fields, and if you want to index all of those, it'll create more index space than the actual data table space. So again, as another reminder, primary key is already a part of the composite index. All right. The next, you always search for the equality. In this example, what would you create an index over here as an example? If you actually follow the best practice as the equality first and the range next. Anyone? Branch ID. Yes, that's correct. So I would actually index the branch ID and then filter. That's actually equality first. If the branch ID is 20, I'll look at the branch ID 20 and then go through all the first name, last name, and the birth date, those. That will go much faster than if you do a first name, last name search. Another best practice over here, 1 index scan is faster than 2. So this is another Percona toolkit over here, duplicate key index checker. This is pretty old, but it's still valid. What we see in the database world is the duplicate indexes. The indexes that are created multiple times thinking that will match the search criteria, like first name, first name. So things like that we see a lot. And if you don't want to deal with that, run the tool. It'll tell you which indexes are duplicate. So another best practice over here. Continue on this one. Numeric for numbers, definitely numeric for numbers. Don't search for string matching over here or character conversion. These are bad. This select is not going to run once. It's going to run millions of times. And if you do like that CPU cycle over here and then convert this value into a character, character to string, string to character, that will cause extra CPU. That will actually impact the optimizer when it actually takes the count into CPU I/O doing the cost analysis. It will pretty much screw up the decision making. So numeric for numeric, strings for strings, and indexing those fields are important. There is another query optimization that we see. So query optimization and indexes are actually linked. Some of the no-nos are these. So if you're actually using negative clauses in your queries, don't do that unless you have to. Do that on the application side, not on the database side, because is not null, not in, not like. These are not very good for optimizer, because optimizer is designed to find the matching criteria. They are not designed to actually match the non-matching criteria. So if you'd actually reverse that, optimizer doesn't like it. So we actually oftentimes see this is a problem, and we change the logic around, things go faster. So just a quick reminder over here, use inner instead of left, because if you use inner join, you'll actually get the intersection. If you do a left join in MySQL, you'll actually scan the first table or scan the second table and find the between. So just a quick reminder over here in the visualization. And another query optimization best practice is union all is better than union. So you're actually, if you're doing a select, union, select. I don't like those selects, to be honest, because I've seen like 13 selects back-to-back unionized to find a value. That's a bad application logic. I don't know how it got there, but for some reason these things happen. instead of doing a union all, instead of doing a union, do a union all. It'll return faster, better for the optimizer. Another optimization best practice over here is that order by can be expensive. So when we actually select the data from the table, you get you want to order by this information. If it's a small set of data, do that in the application side. Application better caches and has a better handle on smaller things. Database oftentimes has to do a file sort, certain sizes, and we don't like the file sort in the database because, as in the first slide, disks are slow. So it's going to do the file sort on the disk. It's going to create a temporary table, and then it's going to sort it. It's going to be slow. So beware of that. Another one over here, order by and limit option. So this is technically called, this is your area as developer. This is the pagination. You actually want to page the data. Doing that in the database is not very efficient. Optimizer doesn't like this also, as it will bring all the data into the memory. It'll cause the buffer pool to fill up with the data that you're actually going to be sorting and using the limit. So watch out those order by and limit operations. And if you can do this in the application side, do it there. Don't do limit. Limits are problematic in the... There is good use cases, but it's problematic in general in the database, MySQL database. Another, okay, we need to go over the index type. Possible index types are these. There's a B3 common, we went over that. There's a fractal tree indexing. That's mostly like TokuDB and TokuMX projects. That's not super common. I don't think anyone over here would even have heard of it. LSM is popular. Elastic LSM, and we saw that this morning. It's log structured merge tree, and it's very popular in MongoDB, Bigtable, HBase, LevelDB. All of those use LSM. MySQL also supports LSM3, but it's not very common to use it. There's R3, geospatial data. So with the version 8, MySQL has done a big remake of this because the popular geolocation, latitude and longitude information to be kept in the database is there's a huge demand in there. There's a hash and there's an engine-dependent indexes also. There's a documentation about it. We don't have actually too much time to get into that. So in the advanced indexing side, I actually put only one slide over here. There's a global query block and table level and index level optimizer hints. There are hints that you can tell to the database using which indexes to, which path to choose. Also, you can kind of force indexes, that's called index hints. Say, use index EI1, ignore index, and order by 2, order by... There is a whole set of syntax for this, just be aware. We can do a straight join, you know, we can force the index until the application can be fixed. These are mostly workarounds to fix the application and the way that the query optimized. Okay. So if the index is not enough, the world doesn't end. There are other solutions. There is a query write technique that is called. There's a tool, very popular proxy tool for MySQL called Proxy SQL. This is my blog. I actually blogged about this earlier this year because this is pretty popular. What you can do, I'll show it in a minute, is to rewrite the query that's coming into the database. So you actually don't change the application. It still comes to the database, but I change it before it hits the database. So basically, it intercepts the incoming query and then changes it, which is mostly an optimization, and then turns the results back. And on 5.7, this is added as a plugin. You can enable, you can add hints and modify the join order. So you can actually basically mingle with the query that's already went into the database. Okay. So we're wrapping up. This is how the Proxy SQL works. If you have questions, I spoke about this a lot. And the final thoughts, 1 minute. Optimizer is not smart as DBAs, okay? So you need to kind of help through that and help the DBA also understand what's happening, what you want to do with the application. That will improve the throughput. Your ultimate goal is to get best out of your database, and the way it's done is to play with the optimizer. And always add the indexes that you need. Avoid duplicate indexes. We spoke about that. And that's overhead for disk space and extra I/O hops. And always stay on the current version of MySQL, because there's a whole engineering department that ideas and development goes into this, as there's several bugs fixed, and the optimizer and the engine improvements are in place for the last few years. And I want to thank everyone for listening. These are the references and credits. I want to highlight this Marcus's book, SQL Performance Explained. This is a generic book. It's not for MySQL. It's written for general MySQL topology, general indexing anatomy, to correct that. I basically read this book for this talk to better understand some of the concepts. And Øystein actually works in Oracle, and he does this optimizer and engine department. I've seen his talks. He gives very detailed talks about that. So there's a nice slide deck over here. Sveta gave me an idea for this. And Jeremy's blog post from 2013 about the global index. And we have some visualization blog posts, and some of these co-workers actually reviewed this talk. Thank you very much for listening.